Okay, we'll wait for the students and we'll start at 6:30. Okay, let us start. So, in this module, I'm going to talk about this last week. I'll talk about the last four videos, which is the so a little bit of Dyson-Schwinger equations. So in this module, okay, so it was covered in this video called the Keldysh contour, and it was just after that. And these are very difficult equations to solve. And then we studied about coherent state path integrals. First for boson, and then for fermions. And then the last two lectures were on non-local operators. These problems will mostly solve are of these. And also, yeah, I will mostly solve of these topics. There, in the last part of the Green's function Matsubara and non-equilibrium chapter in Church's book, there is something about two-level systems, and it's basically time-dependent perturbation theory. The examples in the two-level system, and there is this rabbi oscillation, and all these things can be studied in time-dependent perturbation theory, and it's in any quantum mechanics book. The idea is similar. It is the idea is same actually, but the notations here are a bit different. They're like second quantized notation, but in any book of quantum mechanics, like in Griffiths, you'll find notations which are different, but the idea is similar. How you go about it. So now we'll mostly do problems on these coherent states, the commutation relations, the various proofs that are there in the book. I'll do them as exercise, and the exercises in the book. Yeah, I'll do them. And for these non-local operators, we won't do much problem on this. As you know, it is fully a research topic. So it's most of it is theoretical or hardcore computation, which we will not require right now. Yeah. If anything comes about, I'll just mention it. But one can go through the book and it's there. It's written nicely. Okay. So let's start solving problems. The first question is, given that A dagger has a commutation relation like this, we want to show or argue or verify that A dagger can be written as DDA. Okay. So the notations are a bit different than what has been written in the book. One writes DDZ. To verify that, one can write formally that formally and we are going to do this specifically for the harmonic oscillator. Okay. This is the first part of this question. Number B part is show that A and X on a state N will give you square root of N times minus 1. Okay. Sure. Using the first one. So using the definition in part A. The solution is, since we are asked to verify, I'm going to take any state at n. This can be written as An acted on the vacuum state, and this has a normalization, which is 1 by square root of 1 by square root of n factorial. Now what I'm going to do is I'm going to verify. Right? We have this and we have this. Okay, so I'll take this. Sorry, take this because this is easier. So for the state, if you want to do it with, you have to write this in terms of A if you want to show the opposite. So I'm going to take this. So let me do A acting on any nth state. We'll check with what do you say? Compute this. So this gives us del del A dagger, A dagger acting on cemented intense A square root n factorial 0. So this is the first part, del del A dagger A minus A dagger del del A dagger So what you have is, here you have this thing, and here you have you can now differentiate this, and differentiating this is completely correct. There's no problem with it. And so I will go differentiate this in plus 1 with the formal rules of differentiation. And I have n A dagger minus 1. So this and this, you're going to get A dagger n. So n plus 1 minus n A dagger n square root n factorial 0. This is nothing but 1. So you're going to get back. Therefore, there's nothing but 1. Therefore, whenever you want to test a commutation relation, this is how you do it. You test it on you act it on a test function. This is what I have done. Hence, I'm going and I have gotten this thing as 1. This implies that this thing is 1. Okay. Now comparing the commutation, comparing this with the commutation relation. One can formally write A as equal to A dagger. By the way, this is the same thing which Professor Setlur has written, uh, but the notations were a bit different in the sense that he had taken coherent states, and he had written, instead of A dagger, he had written the differentiation with respect to the eigenvalue of B. So, for example, what I mean to say is we've got Z, Hz, and coherent state is defined as say with respect to A dagger Z bar. So he had written this as ddz bar. Right? Sorry. So coherent state is defined as like this. I'm sorry, and he had written this as. In fact, this is the same thing which I have written. There's no difference here. There's only the notation thing, but it means that only. Okay. Now this is graph. Now what we're going to show is the B part, which is the B part. I have to show that A acting on N is equal to square root N minus 1. So I'm going to start with the left hand side and write A in terms of A dagger, and N can be written as A dagger N times square root N factorial acted on 0. So this can be written as N times A dagger N minus 1 square root N factorial 0. This can be written as N by square root N. I took a N out from here. A dagger N minus 1 N minus 1 factorial 0. So this gives you a root N, and that is nothing but get of N minus 1. Okay. So therefore, we showed that A dagger acting on N, which is equal to RHS. Therefore, we showed that equal to this minus 1. D. So first problem done. Let's do the second problem, and I'll take it from the book. Yeah. Suppose we define. Let me just. Okay, so we are going this definition. Define coherent state as the eigenvalue of the annihilation operator. That is this. Where Z is the coherence state. Okay. And we have got the Bargman representation. Also, Z is equal to e to the power Z A dagger acted on 0 bargaining representation. Show that mm, the two definitions of coherent states are equivalent or consistent. For consistency, we have to show that for equivalence, actually, we have to show that the first one implies the second and the second one implies the first. So we are going to start with one. So we'll take A on Z is equal to A acting on e power Z A dagger on 0. Okay. And now what I'm going to do is I'm going to do the series expansion of this thing. That is 1 plus Z A dagger plus. Okay, there is one more easy way. That is uh, the thing. Yeah. So the easy way, yeah. Okay, that is the actually the proof of the other part. Yeah. Let me do it. So the first is that suppose first is true. Suppose the second one is true. So what I'm saying here is, so what I'm writing is, I'll write this implies this. Proof. First problem. First part. So suppose so what the statement we are making is, suppose this is correct, and to show that this follows. So we will look at A of acting on Z and A acting on e power Z A dagger acting on 0. We'll do the series expansion now. 1 plus Z A dagger plus Z square A dagger square by 2 factorial plus dot 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 acting on 0. Now this is A. This A dagger plus Z square is just a complex number, so and A doesn't operate on Z, so it will just pass through. Now we are going to apply the commutation relation, which is A dagger is equal to 1 plus A dagger A, right? Which says that use that A plus 1 plus A dagger A plus Z square by 2 factorial 1 plus A dagger A dagger plus dot 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 acting on 0. So instead of doing that, what I'm going to do is I'll apply it in a general this thing, and we'll figure it out. We'll figure the pattern, how it acts. Suppose we have something like this. And this implies that this equals E dagger n is equal to E dagger n minus 1. This is 1 plus E dagger n minus 1. This is equal to E dagger n minus 1 plus E dagger. Now we choose E dagger n minus 2. So E dagger n minus 1 plus E dagger 1 plus E dagger n minus 2 is equals E dagger n minus 1 plus E dagger n minus 1 plus this is E dagger square E dagger n minus 3 to E dagger n minus 1 plus E dagger n minus 1 plus E dagger square. This is 1 plus E dagger n minus 3 to E dagger n minus 1 plus E dagger n minus 1 plus that is, so this is 2 plus n minus 3 plus 2, that is E dagger n minus 1 plus E dagger 2 E dagger n minus 3. Okay, so we are going to have here n minus 1s. So if we do it 3 times, we are going to have 3. That means we'll have here, we want to do it n number of times, have n A dagger n minus 1 plus A dagger n, suppose n is 3, 3 minus 3 is 0, A. This is the formula which we are going to have. So I'll just apply 1 in the expansion. Therefore, the first term is just A plus to the power 1 A dagger. So that is 0. So 1 plus A dagger A plus 1 by 2 z square by 2 plus A dagger A. So 1 plus z plus you have a 2 A dagger n minus 1 plus So that is 2a dagger 1. So this is for the second order term. A dagger square A is by 2 factorial plus dot 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 acting on 0. Okay. Now all the terms, oh, A acting on 0 is 0, as is the definition of vacuum state. All right. So this makes it easy. Is equal to everything is 0. All these terms are 0. And we are going to remain with 1, that is z plus, this had a z square multiplied to it, plus z square plus z cube dagger cube by 3 factorial plus dot 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 0. And this is actually, you can take a z out, and this cancels, this 3 cancels with this 3 cancels with the 3. So we have z1 plus a dagger plus z square by 2 factorial a dagger. uh, this was supposed to be a square. So if this is supposed to be a square, because you're going to have one less term. So if it is of power 3, then you are going to have 3 minus 1 2. That is why this comes from the formula which we just found. That is number 1. It's dot dot dot. This is z times e to the power, so z negative acting on 0, which is nothing but equal to averages. So thus we showed that given this, we showed that this is achievable. Now we'll try to show the opposite. That is second part. Given this, you want to show that z can be written as e power z a dagger and 0 given so this seems a bit tricky. Let me think about a moment. Just give me 2 minutes time. So we'll have to start with this only. Now I'm going to operate a dagger on it. Z minus Z. Z divided by Z. So I can see that uh, I have a very I have an idea about it, but this is a very uh, um, this this is correct, but this is not rigorously correct. This is not very rigorous. So I have a proof. Proof is given like this. If I can write this as like this, okay, that means my A dagger can be written as del del Z. Okay. Now look at e to the power Z A dagger 0. Hmm. This can be written as e to the power Z del del Z. This has been borrowed from Sir's notation, which is correct. Not written. All right. Now, here what I'll do is, since these are kets, I want to think of them as a position space representation of some function at the point 0. That is what I'll do is I'll try to associate some wave function with it. Okay. So that means I'll have some x0, and this will give me psi 0 of x. Right, this is very skewed. I think it is a bad. So, so this can be written as like this, and I was going to say that, yeah. So this implies that Ez del del z is equals that. Thing on 0 can be written as 1 plus z plus z square by 2 factorial l square plus dot 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 acting on ket 0, and this can be written as 0 plus z del del z on 0 plus z square by 2 factorial z acting on 0. Yes. This can be thought of as a Taylor expansion with a Taylor expansion or something like this. Okay. This is a very non-rigorous proof, but I think one can bring rigor into it by putting this thing as shy of z. Okay. Can be written as shy of z, and then or like shy of 0, and this is just the this becomes just the Fourier. This becomes just the Taylor series expansion of shy of 0, and you are going to get shy of z, and you take out the position bra which you had add on that shy, and you are just going to write as z. So yeah, the proof. The main thing stems from it that since this is a coherent state, you can write A dagger as like this. So given this, this follows, and once you have got this, then this follows. Okay, let's go. What's up, please? So we showed that these two things are consistent. We will try to show. Yes. Question number 3. Question number 3 is on the exercises. Yeah. Find the or derive the over completeness relationship means relation for the bosonic coherent states. Let me just look at the formula again. First step is to look at this sort of a state. You want to evaluate this. First, evaluate the overlap integral of the coherent state of A and A dagger. Okay. So to do that, we'll look at the matrix element of this quantity. This is equal to, when this acts here, you are going to get Z prime and the same thing. And you can also write this as, you can also write A as del del Z and del del Z bar. And you can put this outside because it won't act on this one. Del del Z bar acting on Z. So from these two, we are going to get is equal to this thing. So from A and B, since they are the same, A comma B implies Z prime to del del Since this only operates on this one, I can pick this out and write this thing. So, so this means that we're going to have a differential equation which implies z prime z bar is equal to ln of z prime, which implies z prime z bar inner product z bar z prime inner product is equal to e power z. Okay. So if there you have any other coherent state with its eigenvalue, any eigenvalue, you're going to have the eigenvalues here, the coherent states here. And look at the ordering. Z bar is here, Z bar is here. So it doesn't matter anyway. These are eigenvalues. Now what you're going to do is, now you're going to write Z is any complex number, and so you're going to come in the normal position basis. And since it is any complex number, you can write this as x plus iy. So I will write z prime as in the prime coordinates and z bar as the complex conjugate. So this is therefore the second rule, write in xy coordinates. So the reason we are going to xy coordinates is because the integrals which we are going to do will factor out. This is it. The Jacobian of transformation is we want to transform from uh, z to x, so we'll have x in the below. minus 2y. I'll put a mod here because I don't want the minus. Just 2y. Therefore, we have dz bar is equal to 2y dx dy. Okay. Now we'll write this thing as, now we look at the integral z prime z bar prime by 2 pi I or minus z bar prime z prime. So I'm just putting this, and I just want to compute this quantity and to see what it gives is equal to e power minus. Now we know this. It is just e power z prime z bar e power uh, omega z prime. Okay. Now I'll do the variable change. So this is nothing but 2y dx dy. So I'll have dx dy and pi below e power minus. Uh, so these are the variables which I know, and this is nothing but z prime and this z bar prime and z prime. These have been multiplied. So you are going to get x prime square plus y prime square. That is, this is nothing but mod z square, not z prime square, which is nothing but x prime square e power z prime is x plus iy. E power z prime is x plus iy. Now we are going to do the integral. Yes, sorry, that is what I was thinking. There is a prime, there is there, there is this, there is this. So there is a, hmm, now this is correct. Now the integral is in terms of x and y, so we can just factor it out. That is to say, we can write one of the integrals just like this. X prime minus x prime minus 2xy plus this is by 4 plus for the plus, so we need a minus and this we get a plus. So we have plus x prime plus omega by 2 whole square. Similarly, e minus delta I uh, minus y by 2 whole square. But here we are going to have a minus sign because of the I. The last term will be mm, a square minus b square because I square is minus. So we are going to have minus b square. Minus and minus makes a plus b square. This minus b square and minus makes a plus. So we have a minus. Okay. So this is what is uy prime. Therefore, we get square root pi by a, which is a square root pi. Similarly, from this integral, from the other integral, square root pi e to the power z prime e to the power 1 by 4 z prime plus omega square minus z prime minus omega square, which is equal to the power 1 by 4 z prime square plus omega square plus z prime omega minus z prime square minus omega square and minus minus plus 2z omega, which is equal to e power omega. Okay. This is nothing but z prime omega. Therefore, we arrived at this solution that this integral can write this inside. which implies that this part is identity. This is the over completeness relationship of the coherent basis. Next 7 5. Now, what I'm going to do is the path integral has been done for the uh, using the coherent state ideas. What I'll do is I will not discuss. If anybody has any doubts, they may ask later. Mm, and now we'll go to fermions, and we'll do some problems in Grassmann number. And let me just bring my other notebook where I have done this, where I have some problems in this. Yeah. And we'll look at the even look at the evaluation of the path integral for this Grassmann variable. Before that, do I want to discuss anything else? Self energy. No, no, that's fine. Okay, let me take a 2 minutes break. I'll just get my coffee. Okay. Ah, okay. And also some of the determinant. Try to have more variables of First is del of C1 and left derivative, so it acts from the left, and I get del L del C1 acting on left, so on. From the right is one. So starting from the left. So I'll have E3. So we have two. Then from the right, equal to E1 minus E3 from the right. Going to encounter for this term, it is going to encounter C2 first. So what you're going to have to do, you are going to have to bring C1 here and C2 there. That introduces a minus sign, and you're going to have a minus sign here, and then it's going to act on C1. This differentiation is going to act on C1, and C2 is going to remain with a minus. Now you will have del R del C2 is just going to be, you're going to act it from the right, but there is no E1 in this expression, so you're going to have just A3. You can have these kind of mixed derivatives when it comes to Grassmann numbers. Okay. Now we're going to compute some. So the commutation relation. Okay. Uh, I'll just give you um, 2 3 minutes to 3 minutes. And seeing this in the video. Take 2 minutes of your time and try solving it. I'll be wise. Okay, let us start. So whenever you have a commutation and decommutation relation of this sort, you are always so this should always you will always use a test function on it, right? Since we know the most general test function, we will apply most general test function on it. That is, I thought C1, C2. So F is this, you left differentiate by C2 then you are going to get this term, and you are going to get minus A3C1. Okay, C1. I'm going to just take this function. So this is equal to C1, C2, A2 minus A3, C1 plus left differentiation with respect to C2 of C1. So you're going to have to take this. So when you take C1, you're going to have A0 C1 plus A2 C1 C2. And the other terms are C2 square, that is 0. So you're going to have this only. This C1 A2 minus A3 C1 square, which is 0, plus here you're going to differentiate. This is 0 because you are differentiating from left with C2, and this will give you minus A2 C1. Since A is just a number, it's not a Grassmann variable. This is just E2, you can pull out common C1 minus C1, which is 0. Okay. This is A. Let's do number B, which is C1 Since this is left differentiation, we don't have a minus sign, just because C1 is on the left already. Plus del L del C1. So this is going to give you C1F. We're going to get A0 C1 plus A2 C1 C2. And this is A1 C1, and this part is just A3 C1 C2 plus A0 plus A2 C2. So this is A0 plus A1 C1 plus A2 C2 plus A3 C1 C2, which is nothing but f of C1 C2. Thus, what you got is C1 C1 is equal to 1. Okay. So combining A and B, we can write Ci del Cj is equal to delta Ij. Yeah, let's do number C. Number C is del C1, del C2 acting on F plus del C2 del C1 1F is equal to first del C2 acting on F is going to give you A2 minus A3C1. This part is going to give you A2 minus A3C1. The other part is going to give you del C1 is going to give you A1 plus A3C2. So this is equal to minus A3 plus A3 is equal to 0. Yes. Now let's try it for the same as well. So this gives just A1 from here and A3 C2 from here. That is A1 plus A3 C2. So that is this is 0. Okay. Since there is never um, a power 2 or higher in F, so a term of this kind, which means that you are differentiating uh, uh, twice with the same variable, will always give you 0. Thus, for any Ci Cj, you'll have this quantity as equal to 0. Now some remarks on integration. Well, I'll just do it as problem itself. So the integration will be something like this. dci dcj is equal to 0. Okay, it's like taking a differential, but the thing is, there was supposed to be a delta ij, that is a constant. When you take a differential, you are varying something. That means that delta ij should also be 0. And similarly, you have this is also 0. Yeah. Now let's look at this. This implies that let's see that it's not how I want to derive the algebra. Also, we have this is 0. This is equal to -1. So using these rules, we have a question. Suppose f is given as f1 is given as a0 plus a1c. Find the first will give you 0, second will give you -1. Is equal to -1. This is 0. We have this as a1. Now, if you remember, uh, this thing is from this rule. If both C's, I's, or J's are same, then CDC is equal to minus of DCC. You're going to have a minus of CDC. That is minus A1 integral CDC. This is again -1, so you're going to have a 1. Now this A1, if you look closely, this A1, let's start with this A1. This A1 is nothing but minus of DDC of F1. This is Right. That is all. So it matters on the convention. So we fix a convention that we always write first. First remark again, integration and differentiation gives same result. To fix the convention, integral dCc. So that is integral of any variable f of c. We will always write it like this. Now we will go to something which we require during the evaluation of path integral. Hence, this is question number 8. Integral of the d eta. Eta were our Grassmann variables. Our eta. This is equal to minus d eta bar d eta bar eta. First term is going to give you 0. Now you're going to write this. You're going to put this here. You're going to have another integral. You're going to put this here. So you swap this. So there is a minus sign. So that makes a plus. And this is 1. This is 1. You're going to get it 1. Question number 9. Suppose eta is a matrix column vector. And this column vector is a Grassmann vector. Therefore, is equal to eta 1 bar eta 1 plus eta 2 bar eta 2. Therefore, exponential of minus eta bar eta is equal to exponential minus one minus square of. The first two terms are going to cancel where we are going to have squares because eta 1 bar square is also 0, eta 1 square is also 0. We are going to just have cross terms, which is eta 1 bar eta 1, eta bar eta 2 plus eta 2 bar eta 2, eta 1 bar eta 1. Now, if we put this here, we have two minus signs, which makes it a plus sign, and again two minus sign, which makes it a plus sign. So this is just so this is the expansion of the exponential. This is question 9a. Question 10 is so this is nothing but beta 1 The first is 0. Second one is also 0 because you are going to couple them, and this is just you don't have all the full variables for this one. Two variables are not there. In this case, one variables are not there. The only remaining term is this term. So this is going through three minus signs. Uh, this is going through three minus signs. 1, 2, 3. So there's a minus 1 and a plus sign. Uh, this goes through. So if after this is gone, there is no this thing. So there is this goes through one minus sign. So there is a plus sign. Now this goes through, both of these are not there. This goes through one minus sign, and this doesn't go through anything. So in the end, we are going to have a minus one. Well, I'll set the convention such that this is a plus one. Oh, sorry. The convention is such that this is going to be one here. Convention. This integral, I've taken it like that. This is a convention. And according to this convention, I will have, so this goes three minus signs. This goes 1 to no minus sign. This goes once, so there is a minus sign. So overall it is a plus and we have a 1. Question 11. Suppose you have eta 1, eta 1, eta 2 defined as some matrix transformation of alpha 1 and alpha 2. Then you're going to have to find so eta 1 is equal to n11 alpha 1 plus n12 alpha 2. Eta 2 is n31 alpha 1 plus n22 alpha 2. Eta 1 eta 2 is equal to n11 alpha 1 plus n12 alpha 2 times n31 alpha 1 plus n22 alpha 2. This is equal to n11 n21 n22 alpha 1 alpha 2 plus n12 n21 alpha 2 alpha 1. All the alpha 1 square is 0 and alpha 2 square is 0. Only these terms remain. And this is nothing but n12 n21 alpha 1 alpha 2. I have changed this. This is a Grassmann variable. So I got a minus sign. This is nothing but determinant of n alpha 1 alpha 2. Okay. Now, from the integration rule, I will just do the change of variables. This is the same as this. Now this implies that so n1 n2 can be written as det n alpha 1 alpha 2. This implies integral d eta 1 d eta 2 can be written as det n. Therefore, this can be written as integral d eta 1 d eta 2. This is nothing but det n alpha 1 alpha 2. Therefore, integral d eta 1 eta 2 should transform as d alpha 1 d alpha 2 by det m, so that this det m and this det m cancel and we get this is equal to this. This is equal to, now we know, now this is equal to this as these are only integration, only dummy variables of integration. Therefore, take this and you apply this, so you go to the result. Okay, good, great. Now this is the last. It's already 8. I'm very late. I didn't even do the coherent state of fermions. Okay, it's all right. I think I covered important stuff though. Okay, the last thing which I want to show is that how we get determinant. Suppose n is equal to m alpha, where n is a two-column vector, alpha is a two-column vector, and alpha is equal to n alpha, m comma n are they are C number matrices. That means the variable complex, they are complex matrices. Not complex matrices. Find the expression for this is an important result, and all the things that I did before was to come to this result. But derivatives and all these things may not have been like it is required if one does high energy theory. Uh, but if one were to do condensed matter, it would not require that much. So, yeah, observation. Solution. So integral, we start with this exponential is equal to this we just saw, we get a depth, and we will have a depth mn. I'll write that a bit later. Now this transform is since we have this integral, we saw how we get it one, and this was one of the exercises which we just did. This was from this exercise from 10. So this implies that it should be equal to d alpha Okay, sorry. This we saw just now from 11, from 10, this from 11. Complex matrices, they're constant. They are not the variables. Call this as A. Then we have, so the determinant of this and determinant of this, they are the same. So we are going to have therefore, the result is still of alpha tilde alpha A, which are, this is an important result when we evaluate path integrals. Anyways, with this, I end the course. I end my time. And yeah, as much as enough. Okay. Thank you for attending. Thank you for watching the video. Uh, and uh, see you later.